Hello everyone, my name is Yali. I'm from San University, China. The topic of my presentation is personalized context-aware collaborative online activity prediction. My presentation will be divided into these 5 parts. First, I'd like to introduce the background of our work. With the increasing prevalence of mobile devices, nowadays users can connect to the internet anytime and anywhere by various apps in their smartphones, thus generating a large amount of online activity data. Naturally, individual online activity contains temporal and spatial information and is highly influenced by these two contexts. For example, in this picture, the user use different apps at different time periods. In the early morning, the user may prefer to use news apps, while in the evening, he may like to use video apps. As for location context, the user is likely to use social apps and video apps at home, while using book apps at the subway. Since users have different online activities in different locations and different time periods, context-aware online activity prediction becomes very necessary. While solving this problem is actually very difficult, there are mainly two challenges. First, the relationship among users, activities, time, and location is pretty complex because for a user, location and time context jointly influence the user's online activity behavior, and for different users, they may use different apps even when they are in the same location and at the same time. So first of all, we should know how to model the complex relationship among users, activities, and time locations. The second challenge is the data sparsity issue, which is often a problem for prediction and recommendation tasks. On the one hand, for each user, we may only observe a small part of his historical online activity. On the other hand, for each user, the scenarios that can be observed are also very limited. Here, the scenario means time and location pair. This causes the data much sparser. Now I will show our solutions. For challenge 1, we propose to build a user location time activity tensor to model such complex relationship. Tensor is a higher order matrix. It is regarded as an efficient way to store context information and can represent a complex relationship among multiple dimensions, so it can be utilized to solve context-aware problem. Like the first picture, the online activity data is stored by a 4D tensor X. For the second challenge, to make up for sparsity issues, we found offline check-in data is very suitable to serve as auxiliary data. Look at the second picture. The check-in data records the user's activity in the real physical world. Specifically, it records the user's visiting behavior toward different POIs in specific locations and time slots. So it contains rich information about time and location contextual knowledge. So we can consider to transfer such knowledge from it to better learn the semantic meanings of time and location context of online activity, then further to help the accurate prediction. Next is our model framework. It includes 3 parts: data and input, generative model, features and output. First, data and input. We consider 2 types of data: online app data and offline check-in data. The app data is recorded as the targeted domain, while the check-in data represents the auxiliary domain. Then we construct a 4D tensor X and a 3D tensor Y, respectively. Then we propose a generative model called collaborative tensor factorization, which is a transfer learning-based method to handle both tensor X and tensor Y, and transfer contextual knowledge among them. Then we obtain all the latent matrices of users, locations, time slots, app activities, and POIs. Then we are able to reconstruct the tensor X to realize the online activity prediction. Okay, now the evaluation results. We use two datasets in our study, telecom dataset and check-in dataset. The telecom dataset records the user's app usage activity during 7 days and it covers about 2,000 apps. The check-in data records users' visiting behavior towards POIs. It lasts for 3 months and its POIs can be categorized into 16 categories. The three figures below show the performance of our model and other methods under different data sparsity levels, and we use three metrics: top 3 accuracy, top 5 accuracy, and NDCG5. Here, the higher accuracy or higher NDCG represents that the prediction is more accurate. We can see that the performance of our model outperforms the baselines, especially at high sparsity levels. For example, on top 3 accuracy, our model can achieve 45% improvement with 60% sparsity level. On top 5 accuracy, 42% improvement, and on NDCG5, 10% improvement. Now we'll conclude our presentation. First, to achieve personalized context-aware online activity prediction, we introduce offline check-in data as auxiliary data to learn semantic information of location and time context. Second, we propose a transfer learning-based collaborative tensor factorization method to jointly model the relationship of different entities and learn their latent feature matrices. Third, our method outperforms the other state-of-the-arts, especially in high sparsity levels. That's all for my presentation. If you have any question, welcome to contact me. Besides, the telecom dataset is available by this link. That's all. Thank you.